So I'm going to talk about WIDON, a wireless MAC protocol we have developed here. I'm Nuno, but this was also done by Bjorn a lot, by Eduardo, and by Ricardo. Ricardo Gomes, which is not here. Okay. So I'll basically talk about the principle behind it, because the principle behind it did already exist in the wired domain, and then I'll speak more precisely about what it is, the protocol, what it is about, and then talk about how we can actually use it in maybe some unexpected or less conventional ways than you would expect to use a MAC protocol. So this principle that we have based the MAC protocol in was a principle that was already existed in the wired domain. So it was designed, these dominance binary compound protocols, they were designed for a wired bus with the intention of resolving conflicts by means of a bitwise arbitration. I will explain what this bitwise arbitration means further on, but basically this was what is implemented. If you haven't heard about dominance binary compound, you might have heard about a controller area network, which basically implements this principle, and it's widely used. It was firstly developed for automobiles, for the automotive industry, but nowadays it's widely spread. It's used in building automation, in industrial control, etc., etc., etc. And there are actually millions of nodes deployed, and you can check that out, that information. So what is this? What is the dominance or the binary compound? Basically, and this is related also to a particularity, or the way CAN also works, is that they give an identifier to each node, and this identifier will act as its priority. So the way this works is when a node wants to access the medium, it will start transmitting first this ID, or which actually its priority, and the wire will act like a logic AND. So when someone transmits a 0 on the wire, no matter what anyone else is transmitting, if someone tries to listen to the wire, it will hear a 0. And this is what we call a dominant. A 0 is a dominant bit. And when someone transmits a 1, the bus will only be in the state of a 1 if no one else is transmitting a 0. Okay. So the idea is this: it's transmitting this identifier bit by bit, but at the same time hear the medium, hear the state of the medium. So basically, if you while you are transmitting your ID, if you are transmitting a 1, but you look at the state of the medium and you see, oh, the medium is in the state 0, I will stop transmitting my priority bits because I know someone else has a higher priority than me, has an identifier that's actually numerically it's lower than mine. So I have here an example of what we call an arbitration. Yeah, sure.
So is this something you're describing which already
yes.
Is like background?
Yes, this exists implemented in the controller area network.
Oh, so CAN
implements this
priority
protocol. CAN implements this bitewise arbitration that I'm describing, and I'll show you here exactly how it works. Of course, then it has all the other things around it, because it's a real protocol. It defines lots of other stuff, timing of bits, how you can actually build a network with it, messaging, etc., etc. But the basic arbitration principle is this. So here I have the example of
Sorry for
nodes.
but what does
Sure.
What does CAN stand for?
Controller area network. I had it in the slide too.
Yeah, I agree.
So three nodes with the priorities or their IDs 4, 2, and 1, and they are contending for the medium, they are transmitting their priority bits. And here I'm ignoring whatever priority bits were here. Imagine that it is defined in the CAN protocol, for example, that you have to transmit 21 priority bits. And here I'm ignoring the other ones, and I'm just saying, okay, this is the part where the decisive priority bits are going to be transmitted. So here, this node is transmitting a 1. So, yes, it is transmitting a 1. So this is a lower level. It's what we call the recessive. It's in the lower level. This is transmitting a 0. It's here. The state is higher. If it was here, it would be recessive. And here it is also transmitting a 0, a dominant bit. So here, these two nodes transmit a dominant bit, and the state of the medium is dominant. So this node is at the same time he's transmitting. He looks at the medium and he says, oh, the state of the medium is dominant, so I know someone else has a higher priority than me. From here on, I will not transmit more bits, I'll just monitor the medium. Okay. So then, moving on, this node is not transmitting more bits, but now we have this node that is recessive, but this one is dominant. Okay. So here again, the state of the medium is dominant, and here this node says, okay, I know someone else has a higher priority than me, I'll stop transmitting my priority bits. So at the end, we only have this node that is still transmitting his priority bits. He actually here is recessive, but he doesn't hear anyone else transmitting a dominant bit. The state of the medium is recessive. So he knows that he has finished transmitting his priority bits, and that he can move on to transmit his message. Okay? And he is the highest priority node in that is trying to access the medium. One important thing, you want to make a question? Go ahead.
What is the medium status? Where does that come from?
It comes from the medium. It's a wire, and you can listen to the wire to see.
But some node must be transmitting that way for the medium to have.
Yeah, like here, nodes are sending a dominant bit. They are putting the state of the wire in a high level. Okay, but the wire, or let's say the way this is implemented, electrically, it's made such that two nodes can do this at the same time, and it will be perceived as a dominant, and two nodes can also, or one node can be recessive. So it is the wire electrically that implements this whole AND mechanism. Okay, is that? So one important thing we will later on see is that when we reach here, even nodes that have stopped transmitting, they are monitoring the medium. So they know what is the priority of the winning node. Okay, and this is important for later on. So now going to the wireless and to WIDOM. So basically the idea of WIDOM would be to implement this mechanism in wireless. So why don't we just do it? Basically there are two things. Is that in wireless we don't have a wire, right? That's probably what it means. And so we have this wired AND mechanism that we obviously cannot implement in wireless. And nodes need to listen while they are transmitting, and this is usually, it's not possible to do in wireless, because if a node tries, even if he could do it, if he tries to hear the medium while he is transmitting, what he will hear is just himself, because his power of transmission will just overcome everything else that other nodes are transmitting. So he won't be able to hear other nodes, he will just hear himself. That's, in plain terms, basically what happens. So this is obviously not possible in the wireless, but you can make a simple observation. You can say, well, but a node only needs to hear when he has a recessive bit, right? Because if he is dominant, he doesn't need to care about other nodes.
It should be recessive.
Oh, this is